So next on our list of reactions to add oxygens to a molecule is a couple of different methods for making what is called an epoxide. Now, we've talked about these before a little bit. We had a question on that in the sample exam I gave you before. I'll put the answer to that in as part of this playlist. But there are two ways to basically create this. The first is a continuation from what we've already done with the halohydrin reaction. It looks like this. We take the alkene, we treat it with something like Br2 and water, which gives us the halohydrin, which is in this case a trans alcohol and bromine. And if we treat that with a base, what we get is a deprotonation here, and then what we get is an internal SN2, so that this nucleophile is coming in opposite to the halide and knocking it out. So that's one way to make an epoxide, is to do a halohydrin and then treat it with base. The other way is a little bit more direct, and the one we're going to talk about here in more detail, which is to use a peroxy acid. So that is RCO3H. We'll do this in one step instead of having an intermediate that we need to isolate. Mechanistically, that one's a little bit difficult to see, but that's what you have me for. So first, the structure. Peroxycarboxylic acids are basically an inserted oxygen into what would normally be our functional group of a carboxylic acid. There are a couple of ones that are commonly used. The most common one that we'll see in textbooks and reference books is metachloroperbenzoic acid, it's abbreviated MCPBA, so this is what it stands for, metachloro. Perbenzoic acid. Actually, it should have a hyphen. And this is what it looks like structurally, which is to say that there's a chlorine here in what is the meta position. When we talk about aromatic naming, that just means a 1,3 substituted benzene is meta. And this is it. Now, there are many reasonable examples of peroxy acids. Why are we always talking about this one? Two reasons. One, it's relatively cheap. Two, the chlorine in the aromatic ring help to stabilize it a little bit, so it's relatively shelf stable. Peroxides tend to be mildly to extremely dangerous in storage depending on the exact structure. So this one's at the very low end of problems. It is reasonably stable on the shelf, so we can store it for good amounts of time without having to worry about it degrading or worse in the flask. So again, there's nothing magical about it. The generic version drawn to the left is just fine, but frequently you'll see the one on the right used. It's not magical, it's just cheap and storable. That's all there is to it. So how does it actually work? I'm going to use a generic version because it's a little easier to draw here. It requires a relatively specific conformation for this to work. So I'm going to draw it kind of pre-folded, because without that it doesn't work. So here's what we're looking at as the twisted up version of that peroxycarboxylic acid. So we have the lone pairs, of course, everywhere here, and we're going to need them. Now, this is, in terms of sheer number of electrons involved, probably the ugliest mechanism in all of Organic 1 and possibly in all of Organic 1 and 2. It has a lot going on at one time. It's all rational, but there's a lot here. I think I'm even going to change the pen color for this, if I can figure out how. First, this proximity of the hydrogen to the carbonyl group is a 5-membered ring. If you count it off, the oxygen of the carbonyl group, 1, 2, 3, 4, 5. That's a reasonable suggestion that something there could be involved, and it turns out that it is. So here's what's going on. One, we have an attack on that oxygen and by that oxygen. So we're forming a three-membered ring. Only one atom of this is involved. What's going on with the rest of it? Well, it turns out that when we attack that particular oxygen, we're also losing its bonding electrons to the other oxygen. That is simultaneously causing a breakage of the carbonyl pi bond, which is then itself taking the hydrogen away from the original. Now, if that's not something that causes you a headache, then clearly you're not paying attention. It causes me a headache, and it's been nearly 30 years since the first time I saw it. I still hate the way it looks. But it does make a certain amount of sense. So just so that we're clear on this, where we end up, I will put the new bond, I'll put everything back where I got it so that we can see exactly where everyone ended up. So I'm going to put every atom exactly where it was before. So I'm going to exaggerate the epoxide a bit here just so we can see it. So here's the atoms that were involved to begin with, some of which are also connected in the same places like this. The others are not. So here's what's happened. Is those existing bonds have ended up here. So this is now the epoxide. That wasn't there before at all. So two of the arrows are making up that bond. This is now where the hydrogen ended up on what was the carbonyl group. And that single bond between the other oxygen and that carbon is now the carbonyl. Now I've been lazy with the electron pairs here, trying to make this a little simpler to draw, but they're all still there. We haven't lost any of our lone pairs. Mechanistically, this is about as ugly as it gets. But it does have some real uses for us. First of all, of course, this is, again, a synchronous reaction. So we're looking at both bonds on the same face. So that's important for us. But what we'll do when we talk about these in a later chapter is specifically epoxides are useful not because they're all that interesting in and of themselves, but they actually give us a way to approach with a nucleophile. So if I treat that with a strong nucleophile, well, that's an SN2 reaction. So I can come in from the opposite side of the oxygen and get this. So I can come in like that and give myself this, which I can then protonate to make the alcohol. So it's a complement in a way to what we've already done. So here's what I mean by that. As I said it before, we tend to look at organic chemistry sometimes as the spoiled child. So here's one way of thinking about that. That if I took this and I did the osmolation reaction, so osmium tetroxide, potassium bisulfite, and the NMO to save me on the osmium expense, what I get is a syn dihydroxylation. So I get both alcohols on what was the same face of the alkene. If instead I make the epoxide with a peroxy acid, what I get is this. What I get is the epoxide where now one side is effectively blocked. Very similar to what we did with the bromonium ion. Now the only way I can do anything with that is to approach the other side. So if I treat that with something like a hydroxide, well, now if I'm going to do an SN2 reaction, which is what this would be, it's going to have to come in opposite. So here we are. Eventually, after we protonate the actually, let's not skip a step here. So immediately we'd have this, and then in the presence of water, well, we'll take care of that and give us the what is now diastereomer of the osmolation product. So it's a way of giving us a complementary product, where if we could only get syn addition from the osmium reaction, here we can actually only get the anti-addition of whatever our nucleophile was and the remaining oxygen. In this case, it's a hydroxide. So we could also have done this under acidic conditions. If you remember that from the past, I could protonate it first and use a weaker nucleophile.